Modern global infrastructure relies on a specific electromagnetic frequency, 1.5 gigahertz. This is the band used by Global Navigation Satellite Systems, or GNSS, to synchronize timing and automate navigation worldwide. On December 25, 2024, Azerbaijan Airlines Flight 8243 was shot down by an air defense system. The incident followed targeted GPS jamming, resulting in 38 civilian fatalities, directly linked to radio frequency interference. By April 2024, the scope of this interference had expanded. In the eastern Mediterranean, 227 maritime vessels experienced simultaneous radar displacement. The spoofed coordinates overwrote the navigation systems of all 227 ships, placing them at the exact same location, the runway of Beirut Airport. A year later, interference targeted the European Commission President's aircraft. Subsequent investigations traced this jamming directly to orbital satellite platforms. This is artificial denial.
It occurs when adversaries weaponize the electromagnetic spectrum to block or manipulate incoming signals. The invisible tether of radio frequency communication is now a primary vulnerability for civilian and military platforms alike. But active electronic warfare is only one way to lose the spectrum. In other domains, electromagnetic denial is an inherent property of the environment. We call this natural denial. Highly conductive environments, like deep sea water, physically swallow electromagnetic waves, absorbing their energy entirely. An aircraft might lose its navigation link because an adversary builds an electronic barrier in the sky. A submarine loses its link because the ocean itself is a physical barrier. Operating in these environments forces a strict engineering choice. We must either manipulate the extremes of physics to force a signal through, or move toward systems that do not require the spectrum at all. Overcoming these two barriers determines whether a platform operates with autonomy or remains tethered to a signal that can be intercepted or absorbed. To understand how the ocean destroys a radio signal, we first look at how we transmit energy over land. Electromagnetic energy travels through standard copper transmission lines efficiently, yet it fails entirely in seawater. When an alternating current flows through any conductive material, the moving electrons induce a magnetic field. As that alternating current fluctuates, the resulting magnetic field also changes. This constant change creates an opposing electrical force, known as back electromotive force, or back EMF. Back EMF is strongest at the very center of the conductor. This internal pressure forces the current outward, pushing the flow of electrons away from the core and toward the outer edges. Physicists call this the skin effect. The alternating current flows only through the outermost surface layer, the skin, of the conductor. This chart graphs the mathematical drop-off in current density as it moves deeper into the conductor. Using the exponential decay formula, we can pinpoint the exact skin depth, the level where current density drops to about 37% of its surface value. The depth of that active skin layer depends on the frequency of the current. As frequency increases, the skin depth shrinks. At standard microwave and radio frequencies, the layer is microscopically thin. Because high-frequency waves are confined to this outer sliver, they dissipate rapidly as heat when they hit a large conductive mass. The medium itself acts as an impenetrable physical barrier. When we apply the physics of the skin effect to the ocean, deep seawater acts as a massive, naturally occurring conductive barrier. If you broadcast a standard high-frequency radio wave into the water, the ocean functions as a Faraday cage. The signal is entirely absorbed within inches. The engineering workaround relies on the math. By drastically lowering the frequency variable, omega, in the skin depth formula, we exponentially increase the depth the wave can penetrate. Achieving a low enough frequency requires massive infrastructure. Governments hollow out entire mountains to house 1 million watt transmitters, generating a 60 Hz signal in the very low frequency, or VLF band. These extreme wavelengths can reach the ocean floor, but their bandwidth is severely limited. A VLF signal can only transmit a few bytes of data at a time, acting as a basic notification to command a vessel to surface for further instructions. This architecture is built to serve a specific platform: submerged nuclear deterrence vessels operating far below the surface. Overcoming natural denial requires scaling terrestrial infrastructure to massive physical extremes. all to push a few bytes of data through the water. In the open airspace, the medium behaves differently. High-frequency signals propagate clearly without the limitations of the skin effect. However, this open medium carries a different risk. Automated navigation relies on external satellite signals, broadcast from 20,000 kilometers away. Adversaries exploit this distance. Operations tracing back to antenna sites along the Kaliningrad coast have turned the Baltic region into an epicenter for artificial denial. State actors have shifted their tactics. They no longer rely on jamming, which blocks the signal with noise. Instead, they deploy circular spoofing. Circular spoofing actively intercepts the 1.5 GHz GNSS signal and rewrites its timing data before it reaches the target receiver. Legacy detection systems fail to recognize the attack. Because the spoofed signal obeys the expected physics of a valid transmission, the receiver accepts the hijacked data as truth. This interference is now migrating from terrestrial antenna arrays to orbital, space-based platforms, expanding the geographic reach of the threat. In active combat zones, relying on an external radio frequency link for position data introduces a single point of failure that adversaries are now equipped to exploit. Protecting navigation in contested environments requires a change in architecture, removing the reliance on the electromagnetic spectrum. The defense sector is developing self-contained quantum positioning, navigation, and timing systems. Rather than pulling synchronization data from satellites, platforms rely on chip-scale atomic clocks to secure internal timing based on the decay of isolated atoms. Standard GPS-guided inertial navigation systems are being replaced by cold atom interferometric sensors. This error rate chart demonstrates the advantage. While traditional inertial systems accumulate drift errors rapidly, the quantum system drifts roughly 5 meters per hour without receiving a single external update. The final component of this architecture is the quantum gravimeter, an instrument designed to map microanomalies in the Earth's gravitational field. Instead of reading a radio wave, the gravimeter navigates by matching local gravitational variances against a highly detailed internal map. It requires 0 external signals to pinpoint its location. Quantum systems create a self-contained navigation loop, immune to electronic warfare and signal denial. These represent 2 distinct engineering strategies designed to solve the problem of signal denial. The response to natural denial relies on massive physical expansion, manipulating the immutable laws of wavelength to penetrate the ocean. The response to artificial denial goes in the opposite direction, shrinking sensors down to the subatomic level to evade adversarial spoofing. While the engineering diverges, both extremes address the same vulnerability, the physical risk of relying on an external electromagnetic connection. The development of these technologies creates a divide between platforms that are self-sufficient and those that remain vulnerable to interference. Operating in these environments depends on a choice: building the massive terrestrial power to force a signal through physics, or the internal precision to navigate without one.